So welcome to this tutorial on bond enthalpy. So really what bond enthalpy is, it's basically just the energy within bonds, okay? Now in your data book you'll find a whole bunch of different bonds, bond types and their energies. Now bond enthalpy really comes into play when you talk about chemical reactions and energy being released or absorbed. So really the ideas that we're going to focus on are exothermic and endothermic reactions. Okay, so what I'm drawing right now are the energy profile diagrams for these reactions. So over here on the left is our exothermic reaction. All right, and here is our endothermic reaction. Now what we need to remember is that these profile diagrams are showing you, first of all, on the x-axis, this is like duration or time. So as the reaction progresses, this is the energy change. So the y-axis is energy. There are a couple of sections on this graph which are really important. We all know about the regular ones. We all know about the delta H. Okay. And delta H, we can define that as the change in enthalpy. Okay. And it's calculated by determining the difference between the energy of reactants and products. Okay, so if delta H goes down, okay, so we started at this point, we're going down to this point, then our enthalpy change is negative. If delta H goes up, then our enthalpy change is positive. Okay, this is a positive change, and this is a negative change. All right, so we know delta H. We also know what the activation energy is. All right, this is all stock standard stuff. Okay, the activation energy. Now for the endothermic graph, it goes from, for any graph really, so it goes from the energy of the reactants to the energy, or to the peak of the graph. Okay, so this would be the activation energy for the endothermic reaction. All right, and so yes, just to specify, this is the reactants energy and this is the products energy. Okay, so this is the reactants energy. So this level here, this line, is the reactants energy, and this is the products energy, this line here, or this level here when you read it from the graph. Okay, now what we need to know now is, or what we should know, this is just a reminder, is that in order for this whole thing to occur, in order for our reactants to be converted into products, okay, for our reactants to be converted into products, energy is absorbed and energy is released. Now, the point of the graph where it is going upwards, so this is the energy of the reactants, the point where the energy starts to increase, okay, this point, bond breaking process. This is bond breaking. Okay, so energy actually needs to come in. Energy is increasing. Energy needs to come in, needs to increase in order for the bonds to break. Bond breaking equals energy in. Okay. Now, as energy starts to decrease, so from this point onwards, Actually, I'll do this in a different color. So as the graph starts to go down, okay, energy is actually leaving, energy is going out. This is the bond forming process, and this is energy out. Okay, so energy in versus energy out. So what does this actually look like? Well, what it is basically is, imagine that you have a simple combustion reaction. So CH4 plus oxygen. This will give us CO2 plus H2O. Right? Okay, I don't know why I circled those ones. Okay, so this will give us CO2 and H2O. So a chemical reaction, CH4 plus O2 gives us CO2 plus H2O. Alright, and we can go ahead and balance the reaction out. Carbons are balanced. We need to balance out the hydrogens. And then we need to balance out these oxygens. So 4 oxygens, 4 oxygens. Okay. Now, in order for these reactants to be converted into these products, what we need to happen is for all of these bonds to break and rearrange. Okay. So these bonds, actually I should have done them in blue. So let's do them in blue, because this is going to require, this is bond breaking, this is energy in. Okay, so this is going to break, this is going to break, this is going to break, this is going to break. Every single bond is going to break. So I should actually fix that up. Okay, this should be a double bond. Okay, now we're going to be breaking in O double bond O. Okay, so in total we have broken, we have broken 4 CH bonds. We have broken 4 times the CH bond, and we have broken also 1 times the O double bond O bond. Okay, now on the other hand, we have formed new bonds. Okay, we have formed a CO and another CO, C double bond O, and we have formed an O, an OH, and another OH. Now I just realized something as well. We need to take into account these coefficients. Okay, so what we've drawn in this equation, let's just copy that. Let's copy these coefficients up here so we can make sense of it. So there are 2 of these. Okay, and there are also 2 of these. So actually, okay, we don't just have one O double bond O, we have two O double bond O's, and we are going to form 2 CO's. So we're forming 2 times the C double bond O's, and we're forming 2 of the OH's, OH bonds. Okay, now we can find the values for these bonds, the energy in these bonds, in the data book. Okay, now as you can see, this CH bond over here, CH bond, it contains 414 kilojoules per mole. Okay, now we got 4 of them, so really we need to add 414 multiplied by 4. Okay, this is how much energy, 414 kilojoules per mole. We got 4 bonds. Okay, so we need 4 times that. Plus, we need to also add 2 of these O double bond O's, which is right here. Okay, O double bond O, 498 kilojoules. So we need to add 498 times by 2. Okay, we do that on our calculator. And what do we get? We get the add in 2,652 kilojoules of energy. All right, this is how much energy needs to come into the system to break these bonds. Now over here on this side, okay, we've got the C double bond O's. So C double bond O's is here. Okay, let's not get confused. These are single bond enthalpies in this table, and these are multiple bond enthalpies in this table. Okay, so C double bond O is 804, so that's 804 multiplied by 2, because we have 2 of them being formed, and we've also got OH bonds. Now the OH's is right here. Okay, OH is 463 multiplied by not just 2, oh my god, 4. Okay, so this is 4. We need 4 of them. 4 of them break, because there's 2 in 1 and we got 2 of them. Yes, okay, so 463 times by 4. Okay, so we add that up. 804 times by 2 plus 463 times by 4, that's 3,460 kilojoules. This is how much energy goes out. This is how much energy goes in. Okay. So what we can figure out is delta H. Okay, so this much energy, let's focus on this graph over here. Okay, so in other words, let's write them down. So 2,652 kilojoules, 2,652. This upwards part of the graph is 2,652 kilojoules. That how much energy goes into the system. Now, going out of the system, okay, the red line, how much energy was that? That was 3,460. 3,460. 3,460 kilojoules. We can find the difference between these two numbers and we will get delta H. Okay, so the theoretical delta H then, delta H is going to equal to 2652 minus 3460. Okay, 2652 minus 3460. That's about negative 808 kilojoules, okay, per mole. Okay, delta H is negative 808 kilojoules per mole. That's the theoretical enthalpy change. Now, okay, so the important notes are, make sure that when you do this method, okay, you draw out the structural formulas of all of your reactants and all of your products. And like I showed you, it's very easy to forget to factor in these coefficients. Okay, so you want to make sure that you have the coefficients there, so you know how many bonds you are breaking and how many bonds you are forming. And it's just a matter of making sure you identify all of them, okay, and you quantify how many are broken. You look at the item in the data book, so item 10 and 11, work out the energies in each bond and total sum all of the energies together. Bond forming is energy in, bond breaking is energy in, and bond forming is energy out. Okay, so hopefully this little video on bond enthalpy helped you out a bit. This is almost 100% going to come up on the exam in some way, shape or form, because it is new and VCA wants to assess it. Any questions, please feel free.